Have you ever wondered how we can describe something as huge as the swirl of a galaxy and the flow of a tiny river using the exact same set of rules? Well, it turns out there's a special language for that, a kind of mathematical poetry for the physical world. And today, we're going to learn its name, vector calculus. I mean, that's a huge question, right? The world feels so impossibly complex. How do you even begin to write down the rules for forces you can't see, for motion in 3 dimensions, for fields that fill up all of space?
It turns out there is a common language for all of it. And by the end of this, you're going to understand its fundamental grammar. We're going to decode the principles that literally govern our physical reality. Okay, first things first. Before we can describe any kind of motion or fields, we need the basic tools to just describe space itself. You can think of these as our foundational nouns and verbs. Okay, let's dive into this, because this is cool. In vector calculus, there are 2 totally different ways to multiply vectors. First up, the dot product. It just asks a simple question. How much are these 2 vectors aligned? And it gives you back a single number. That's it. It's just a measure of their agreement. Then you've got the cross product, which is a completely different beast. It takes 2 vectors and gives you a brand new vector, one that's perfectly perpendicular to the first 2. It's all about creating a new direction out of thin air. So why on earth do we need both? Well, because they describe completely different physical actions. The dot product, that's perfect for calculating work. So think about it. If you push a box, only the part of your force that aligns with the box's motion is actually doing any work. That's a dot product. And the cross product is all about rotation. When you use a wrench, you apply a force to create a turning effect. We call that torque. That torque acts along the axis of rotation, perpendicular to both the wrench and the force you're applying. You guessed it, that's a cross product. All right, so we've got our static tools down. Now let's add the magic ingredient, time. This is where calculus breathes life into our 3D world, and we can start describing things that are actually moving. So just imagine a fly buzzing around a room. We can describe its path with a function that tells us its position vector at any given time, t. And at any single moment, its velocity vector points exactly where it's going. It's always tangent to its path. Its acceleration vector, well, that points in the direction of the force it feels. It's what's causing the fly to speed up or slow down or make a sharp turn. Now here's something that's really, really interesting. Acceleration isn't just one thing. When you're in a car, tangential acceleration is that feeling of being pushed back in your seat when you step on the gas. It's a change in your speed. Normal acceleration, that's the force that shoves you into the door when you take a really sharp turn. It's a change in your direction, even if your speedometer doesn't move. Physics has to separate these 2 things, and vector calculus gives us the exact tools to do it. So far, we've been focused on just a single particle moving through space. Now, let's zoom out and look at the space itself. I want you to imagine an invisible landscape of forces all around you, like a wind map, a magnetic field, or the current in a river. Vector calculus gives us these amazing operators to describe the shape of this landscape. First up is the gradient. So imagine you're standing on a hillside. The gradient is simply a vector that points straight uphill. It's the direction of the steepest, hardest climb you could possibly take. It packs all the information about the slope right where you're standing into a single, elegant arrow. And in physics, this tells you the path of greatest change. Next up is divergence. This tool measures if a point in a field is a source, where stuff is coming from, or a sink, where it's all going. A point with positive divergence is kind of like a sprinkler head, with flow just radiating outwards. A point with negative divergence is like a drain, with all the flow pouring inwards. And if the divergence is 0, simple. What flows in must flow out. And finally, we have curl. This one is my favorite. Imagine placing a tiny, microscopic paddle wheel into a flowing river. The curl vector tells you exactly how fast and in what direction that little paddle wheel would spin. It measures the tiny, swirling, rotational quality of the field at every single point. It's how we find all the hidden whirlpools. Okay, we've got our tools. We can describe motion, we can map out fields. Now for the grand finale. Let's see how all of these ideas, gradient, divergence, and curl, come together in one of the most beautiful and frankly profound patterns in all of mathematics. Just look at the pattern here. It all starts with something you probably learned back in school, the fundamental theorem of calculus. For a simple 1D line, the total change that happens inside is measured by its 2 boundary points. Now let's scale it up. For a 2D area, all the rotation happening inside is measured by the flow around its boundary curve. And in 3D, all the sources or sinks inside a volume are measured by the total flow across its boundary surface. Do you see it? It's the same idea, just playing out over and over again in higher dimensions.
So what's the big takeaway? The crucial point is this incredible, repeating idea. It doesn't matter if you're talking about a line, a flat area, or a whole volume of space. You can understand everything that's happening on the inside by just looking at what's happening on its edge. The information is all encoded on the boundary.
This is not just some clever math trick. It's a deep, fundamental truth about our physical world. This connection between a region and its boundary is really the philosophical heart of vector calculus. It's the backbone for huge areas of physics, from fluid dynamics all the way to electromagnetism.
And that leaves us with a really fascinating question. If the secrets of a volume are written on its surface, and the secrets of a surface are written on its edge, what else can we understand about our world, about systems, maybe even about ourselves, just by paying closer attention to the boundaries?